It's my great pleasure to start today's seminar, Computability Education. So before we start with today's talk, I would like to mention that already scheduled further seminar talks next week and after. 9, we will have Nikolai Bachenov in our seminar, and on June 6th, you can find the exact titles and times in our calendar. But today we are going to hear a talk from Vittorio Bard from the University of Turin. I'm curious what he is going to tell us on a local approach to uniform margins. So please go ahead.
Okay, thank you very much. And thank you for inviting me, and thank you to everyone for attending this seminar. So I'm going to talk about this work that is partly joined with Patrick Lutz. And I will start with an introduction to Martin's conjecture. So everything started with the observation that Friedberg and Muchnik's solution to Post's problem doesn't provide a canonical way of taking given degree x, intermediate c degree between x and its jump, because the map that is provided by the proof needs to take a representative in that degree and gives us a intermediate C set. But the degree of this set could change accordingly to the representative that I choose in the degree. Okay, so what Sachs asked in 1967 is if we can find a solution to Post's problem that is provided by a CE operator that induces a function on Turing degrees. Okay, so this question can be phrased as, is there a degree invariant solution to Post's problem that preserve Turing equivalence are called the degree invariant? So in some sense, Sask was asking if there is a natural solution to Post's problem. And Martin's conjecture is just was aiming at generalizing Sachs' question and also providing an explanation to the empirical phenomenon that the Turing degrees that we find in mathematical practice seem to be well ordered by Turing reducibility, and that the Turing jump seems to be the successor in this well order. We, of course, all know examples of this phenomenon. My point here is that all these examples relativize to an arbitrary oracle. So the idea under the formalization of natural degrees in Martin's conjecture is that natural Turing degrees have a definition that relativizes, and so they actually provide definable degree invariant functions. So maybe we see this well ordered in natural Turing degrees because the structure of non-trivial definable degree invariant function is essentially well ordered. You see here that I put some words in italic. These are the vague words that I have to explain in order to give a precise formulation. So, first of all, definable in this context means any function under the axiom of determinacy, okay? Because this axiom implies that all sets of reals, and so also all functions over reals, are regular, non-pathological. And then essentially here means up to Martin's measure. So I have to tell you what the Martin's measure is. So first of all, Turing determinacy is the statement that every set of reals that is closed under Turing equivalence we call these sets Turing invariant, either contains a cone or its complement contains a cone, where a cone is a set of this form, the set of all reals that can compute a fixed real. And the fixed real, in this case Z, will be called the base of the cone. Okay. So a theorem by Martin is that this is a consequence of the axiom of determinacy, and indeed it's a very important consequence, because under Turing determinacy we can define this measure on the family of Turing invariant sets of reals that is called the Martin measure, that gives a measure 1 to a set when it contains a cone, 0 when it's disjoint from a cone. Okay. So now, given functions, we can define reducibility almost everywhere and equivalence almost everywhere. Okay, that is on a cone. And the intuitive idea behind Martin's conjecture is that, like we said, natural Turing degrees induce some intuitively natural degree invariant functions. And also under AD, there aren't many ways to cook up new degree invariant functions, because we don't have, for example, the full axiom of choice. We have dependent choice, what we can use. So, for example, we could patch together countably many degree invariant functions into a new one. But in this case, under Turing determinacy, one of the pieces would prevail on a cone. Okay, so the idea is that if we mod out by equivalence on a cone, we should morally obtain the set of natural Turing degrees. Actually, we should work just with non-trivial degree invariant functions, because if you consider functions that are constant almost everywhere, and you mod out them by equivalence almost everywhere, and you order them by reducibility almost everywhere, of course, what you find is, again, the structure of Turing degrees. Okay, so we want to exclude these trivial functions. So Martin's conjecture is formulated under these axioms, okay, and it's divided in two parts. The first part is telling us that if a function is degree invariant, either is a constant up to Turing equivalence on a cone, that is trivial in this case, or if it's not trivial, it has to have this property that f of x can compute x almost everywhere. Okay. The second part of the conjecture says that the functions, the set of functions having this second property is pretty well ordered by reducibility almost everywhere, and if in this pretty well order a function has rank alpha, then its pointwise jump has rank alpha plus 1. Okay. So in particular, part 2 of Martin's conjecture would imply a negative answer for such questions, because not only there can't be CE operators strictly in between the identity of the jump, but any function whose existence can be proved in ZF plus DC plus the axiom of determinacy, if it's above the identity, then it's in this set, so its rank has to be, if it's 0, it has to coincide with the identity. Otherwise, if it's greater than or equal to 1, it has to be above the jump. Okay. So now we come, I have to tell you what is uniform Martin's conjecture. So first of all, say that x is Turing reducible to y via I if the ith computer program computes x when it uses y as an oracle. of course. And then similarly, we define what it means that X is Turing equivalent to Y via the pair ij, okay? And now we say that a function is uniformly degree invariant if there is a function u from pairs of natural numbers to pairs of natural numbers such that whenever X is Turing equivalent to Y by ij, then the images f of X and f of Y are Turing equivalent via uij. So essentially I can choose this witness of f of X and f of Y being Turing equivalent uniformly in X and Y, okay? So the function u here is called a uniformity function for f. And if f, when it's degree invariant, it's a morphism of the relation Turing equivalence, we can think of the couple f and u when f is degree invariant uniformly and u is the uniformity function as a homomorphism of the two-sorted relation Turing equivalence via. Okay, I have a function for each sort and the relation is preserved. Okay, so it's a natural concept to consider, but it's also a very useful one. For example, Lachlan, who introduced uniformly degree invariant functions, proved that there is no uniformly degree invariant solution to post problem. So if we had the requirement of the CE operator in Sachs question to be not only degree invariant but uniformly, then we can give a negative answer. And still went on and proved that this is actually because the whole part 2 of Martin's conjecture holds for UDI functions, okay? And again, later, jointly with Sleman, he proved that actually the whole Martin's conjecture holds for these functions. And then there are other results that show how interesting are uniformly degree invariant functions. Here I just put 2 results to give an overview that show the connection between these functions and descriptive set theory. I'm not going to give details about this. I just wanted to point out that they are a crucial object in this field. Also because under AD, they are essentially the only degree invariant functions that are known to exist at the moment. Okay, indeed, there's this conjecture by Steele that under AD, every degree invariant function is equivalent almost everywhere to a function that is uniformly degree invariant on a cone. And this conjecture in particular implies Martin's conjecture. Okay, so now we come to the local approach. Local approach essentially means that we are looking at uniformly degree invariant functions defined just on a single Turing degree, okay, which is a very not conventional approach because in this field in the context of Martin's conjecture, people are usually interested in seeing what happens on a cone, right? On a measure 1 set. And single Turing degrees are, of course, measure 0 sets. But nevertheless, it will, I think, I hope I will convince you that it might be interesting to, for example, ask the following question. What are the possible degrees of the range of a UDI function that is defined on a degree X, okay? Of course, any degree in the cone above X can be the range of this function. For example, if we consider the function that takes z to z join y. Are there other possibilities? The answer that we are going to give is no. Indeed, we are going to prove this result that says that, well, if I have a UDI function on starting from a degree x, of course, if it's constant, it's UDI and it can go to every Turing degree, okay? But this is trivial. But if the function is non-constant, then it necessarily has to go to a degree in the cone above the degree of x, okay? And this can be viewed as a local version of Sleiman and Steele's theorem. And indeed, we are going to show that it implies it. And it implies it also in providing a simpler proof. In particular, we can avoid using games like in the original proof. So we can avoid using the whole axiom of determinacy. We can just use Turing determinacy. Okay, we can just use Martin's measure. And before proving the theorem in the local version, I would like to show you how easily this is done. So let's assume the theorem and let's prove the corollary. Of course, the set of Turing degrees is partitioned in two parts: the degrees on which the restriction of f is constant and the degrees on which the restriction of f is not constant. So one of these sets has to contain a cone. So if there's a cone of degrees in which the restriction of f is not constant, by the theorem, we have that in those degrees, f of x has to be above x. And so we have the thesis, okay? Otherwise, we have a cone of degrees on which we have this property, okay? That f maps the whole degree into a single real. And in this case, it's easy to see that the function has to be constant on a cone, because two reals in this cone, if they are in the same degree, they agree in particular on what should be the kth digit of f of x. So the set of reals that give the same digit to f of x is closed under Turing equivalence. So by Turing determinacy, the kth digit of f of x has to be constant on a cone. And this holds for all k. So if I go in the intersection of these countably many cones, this contains a cone, and in this cone, every digit of f of x is constant. So f is really constant, okay? Great. So this actually gives us the following meta-mathematical result, that part one of Martin's conjecture is actually equivalent over zf plus dc to Turing determinacy. Now we have seen that it's implied by it, but it's also very easy to see that there is also the reverse implication. And it's so easy that I'm not going to do it. Now the natural question is of Martin's conjecture from some local phenomenon, okay? And the answer is that we still don't know, but the forefather of part two of Martin's conjecture can be proved by local phenomenon. And I'm talking about Lackland's result, okay? So we are going to show that Lackland's result can be followed by this local theorem by myself and Patrick Lutz, okay? So what we are going to do is we are going to prove these two local theorems. we are going to discuss further is if part 2 of Martin's conjecture arises locally. Then we are going to talk about some open problems. And I hope to have time.
I have a question, sorry. So could you show me the theory again that you proved?
Sorry?
The equivalence, the uniform, the part 1 of Martin's conjecture and the TD.
Yeah.
I think Steele and Slam, they proved, they need AD to prove the part 1 of uniform Martin conjecture, not just TD.
Yeah, indeed. Slayman and Steele need full AD, but like I said, one of the advantages of these approaches is showing that actually their theorem can be improved, showing that it follows from TD alone. Yeah.
Okay.
And
nice.
yeah,
okay.
Sure.
Okay.
And okay, so last thing that I hope I will have enough time to do is showing an application to computable reducibility. So let's start with the proof of the main theorems, and we will need this lemma that says that if I have a UDI function on a Turing invariant domain, then I can choose a computable uniformity function for it. Okay, and the proof is actually not hard, but I'm not going to do it for reasons of time. I'm just going to just give the idea. So there are finitely many Turing reductions that when they are composed, they can simulate the behavior of any Turing reduction. And if I know the value of the uniformity function on these generators, I can computably reconstruct the global behavior of the uniformity function. Okay, so this is essentially the idea that we use in the proof. But let's assume the lemma and let's prove the theorem. Okay, so let's suppose we have a UDI function from the degree of x. Let's suppose it's not constant, so let's pick y in the degree that has a different image, and we prove that f of x can compute x. Okay, so since f of x and f of y are different, say that they differ in the kth digit. Without loss of generality, suppose that the kth digit of f of x is 1 and of f of y is 0. Otherwise, we just switch x with y. And we define this sequence that we can see as a characteristic sequence for x. Okay, and not only it is a characteristic sequence, but also when I take the image of it, since f of x and f of y are different, they are going to simulate the alternance of the digit of x. And actually, if I look at the kth digit of the sequence of the images, I just find again x. Okay, and also notice that there is a computable function t and a fixed reduction e, such that x is Turing equivalent to xn via tn e. So this should be easy to see. Okay. Now we take a uniformity function for f that is computable, and I can do it by the lemma. And what I get is this other line for the definition of the uniformity, okay? But this in particular is telling us that f of x can compute f of xn via the first one of the two coordinates of u, tn, and d. That is, I have this last line. But now I'm done, because x is exactly this function here, because this guy is just the kth digit of fxn, and the kth digit of fxn is just the nth digit of x. So this function here is just x, and this function is computable in f of x because the function that I have here in the subscript is a computable function because u, t, and the projection are all computable functions. Okay, so we are done. X is computable from f of x. And now let's prove also the other result about CE operators. So this is joint with Patrick Lutz. Suppose we have a CE operator that is uniformly degree invariant on the degree of x, which is greater than or equal to 0 jump. Then what we have is that if WE is discontinuous in a point of this degree, then WEX has the same degree as X jump. Otherwise, if it's continuous in one point, then we have two possibilities. Either the operator is constant and constantly equal to a CE set on the whole degree, or WEX has the same degree as X. Okay. So for the proof, the first thing that we notice is that for all m, we have that the mth digit of WEX is 1 if and only if it's 1 in a whole basic open neighborhood of X. Okay, so the CE operators are semi-continuous. They are not always continuous because, of course, this is not always the case when the mth digit is 0 instead. Okay, so the continuity in X amounts to say the following. Okay, and notice that okay, suppose first that WE is continuous in X, then this property is decidable in 0 jump, and so by hypothesis is also decidable in X. So by this if and only if, that is the continuity, we have that the complement of WEX is C in X. Okay, of course, since this is a CE operator, WEX is also C in X. So by post theorem, WEX is computable in X. Now we want to say that either it has the same degree as X or it's constant. We use the previous theorem. So because this is uniformly degree invariant. And so we have these two possibilities. Either it's constant on the whole degree, or WEX is greater than or equal X. So in the second case, we are done. In the case in which it's constant, it's not hard to see that it has to be constant to a CE set, because in this case we have that WEX M is 1 if and only if there is some Z in the same degree of X and some initial segment of it for which it's 1. But since the set of initial segments of things that are Turing equivalent to X is just the set of all possible finite sequences, we find that WEX is constantly equal to this set, which is C. Okay, and so we have the first half of the statement. For the second half, suppose now that WE is discontinuous in X. Okay, so in this case, what we have is that for a certain M, the nth digit of WEX is 0, but for all initial segments of X, we have a sequence extending that makes WEM V1. Okay. And of course, there is an effective procedure that, given an initial segment of X, finds the first tau for which that computation converges. Okay, so let's call tau with the subscript sigma, the tau that is found by this effective procedure given sigma. We also denote with this notation the Lth approximation of the jump. And what we want to do now is to construct a characteristic sequence for the jump of X. Essentially, we want to have a similar argument sequence to be Turing equivalent to X, and we want to witness this with a sequence of computable indices. And then we will use the computability of the uniformity function to make sure that the images can, WEX can compute the real that is coded by this characteristic sequence. For have this characteristic sequence, we also need not only that the sequence is made by different things, but we also need that the images via the operator have to be different. And we make it sure by doing the following thing. If n is not in the jump, the nth element of the sequence will be X. And so the nth digit of the image will be 0. Otherwise, I will attach, when I find out that actually n is in the jump, then I attach a tau that makes sure that the image is going to have the nth digit equal to 1. Okay. And then in the end, I attach an X that has the role of making sure that this real is in the same degree as X. Okay. So what I'm claiming here is that this can be do computably, that there is this computable function Rn that makes this work. And also, it's not hard to see that there is a function that is computable Sn that given Xn gives us back X. Okay, it shouldn't be too hard to see. And like I said, now we are done because we have X that is Turing equivalent to Xn via Rn Sn with this computable, and we are in this situation in which the nth digit of and we let vary the n in the characteristic sequence. This codes the jump of X. So like before, the argument gives us the WEX can compute X jump, and of course X jump can also compute WEX. So we have that they have the same degree. Okay. Now we come to the open question. The main one is if also the second part of uniform Martin's conjecture, that is Steele's theorem, arises from some local facts like the first part. Well, the main problem here is the fact that we mentioned that when we have a degree invariant function from a single degree, every possible degree in the cone above that degree can be the possible range of that function, and that function can be taken to be also continuous, because I can just take the function that maps z to z join y, like we said before. Now, the point is just this. Maybe if we think of the theorem that we just proved, there we had that if the function is discontinuous, then I can say that it has to be above the jump. Okay, so this will be the idea. So for the sake of this talk, I will stick to just Steele's theorem for Borel functions that can be rephrased like this. For any countable ordinal that we fix alpha, if we have a Borel UDI function that has the property that f of x can compute x on a cone, either there is beta less than alpha, such that the f of x is computed by x to the beta on a cone, or f of x can compute x to the alpha on a cone. And notice that, for example, if alpha is equal to 1, what we have is we are saying either f of x is less than or equal x on a cone, or f of x is above the jump on a cone. So, like I said, of course, I can't expect this to happen also locally, because locally also every intermediate degree can be the range of local UDI functions. But notice that being f of x being less than or equal x on a cone is implied by f being continuous on a cone. Okay, so maybe that is what happens on a cone, and is the continuity. Maybe that is the point. And also, when alpha is not 1, of course, we know that Borel functions are stratified in a Baire class alpha for each countable ordinal alpha. Continuity is just Baire class 0, and f of x being computable from x to the beta on a cone is implied by f being Baire class beta on a cone. Okay, so the question that we ask is, if we fix a given alpha, countable ordinal, and a degree with respect to which alpha is computable, is it true that given a Borel UDI function f on that degree, either f is Baire class beta for some beta less than alpha, or f of x can compute x to the alpha? Okay, so this is the question that might be what implies from a local perspective Steele's theorem. And the second question that I wanted to ask is, what about the theory of each single degree as regarded as a two-sorted structure with Turing equivalence via? Okay, so what we know is that this theory has to stabilize on a cone by the argument that I told you before, but there are lots of things that we don't know about this theory. For example, is it a decidable theory? What is in general, the Turing degree of this theory? And also, can we characterize the Turing degrees having this theory? So one remark is that when we consider Turing degrees with the language of Turing reducibility via, then we can write a very simple sentence, this one, that is true when it's interpreted in the computable Turing degree, and is false in every other degree. Okay, so this is telling us that with this language of Turing reducibility via, not all Turing degrees are elementarily equivalent. But here I'm asking if with the language of Turing equivalence via, all Turing degrees are elementarily equivalent. Okay, so this is the second question that I wanted to ask. And since I have 5 more minutes, I have time to mention also this application to computable reducibility. So very briefly, if we have 2 equivalence relations on natural numbers, we say that E is computable reducible to F when there is a computable function. That is called a computable reduction that makes this job here. And now, given an X, we can define this equivalence relation on natural numbers that identifies to natural numbers when they are indices for the same partial computable in X function. And the theorem is that the map that takes X to this equivalence relation in X is a Borel reduction from Turing reducibility to computable reducibility. That means that we have this if and only if. Okay. So the proof is easy in the left to right direction, and in the right to left direction is just a variation on the same argument of before. Because if we have a V that is a computable reduction from this equivalence relation in X to the one in Y, then we can define an F that goes from the set of partial computable in X function to the set of partial computable in Y functions that is defined like this. And this is a well-given definition because it doesn't depend on the index I that represents this partial computable in X function, because V is a reduction between these two. And also, since a reduction is an if and only if, this also tells us that this function is injective. And what we have is also this implication. I'm just rewriting this fact. I'm saying if Z is Turing reducible to X via I, so if Z is this guy here, then its image via F is Turing reducible to Y via VI. Okay, it's just this equation. And this is enough to carry the same argument of the local Martin's conjecture uniform part 1, because we can build a characteristic sequence, and we have that V is computable, and we have this implication. We have it with Turing reducibility instead of Turing equivalence, but this is enough, because if you remember, in the previous proof, we took the projection because we just needed one direction. And the only subtle point here is that we have to be a little bit smart when we construct the computable reduction, because I mean the sequence, the characteristic sequence, because these two objects are partial functions. So if they differ, it doesn't mean that on one digit I can see that both are defined and different, but it will be that one is defined and the other one might diverge. But we can anyways do it if we take a characteristic sequence not for x but for x join x complement. Okay, so also in this case with the same argument we can see that y implies x, y computes x. Okay, and so we have this with this corollary that we can embed the Turing degrees into equivalence relations as ordered by a computable reducibility. So we can transfer a lot of our knowledge about Turing degrees into this subject of computable reducibility. And okay, so the last question that I ask is, since we have this Borel reduction, is if this locally countable Borel equivalence relation is actually universal. So this is the case actually for all locally countable Borel quasi-orders, that they actually all Borel reduce to it. And this was the last thing that I wanted to say. Actually, the second last one, because the last one is thank you for your attention.
Okay, thank you very much, Vittorio, for your very interesting talk. So we can only give you a virtual hand clap, but I guess there are some hand clap signs as well. Are there any questions from the audience? So Liang Yu, please go ahead with your question.
How about the second part? Have you thought to use TD to prove the second part of Martin's conjecture?
I mean, this is a subtle point because actually when I ask this question here, it's not clear if it would actually imply Steele's theorem. We know that it would imply, for example, if we take alpha equal to 1, then we know, if we knew that locally all the UDI functions are either continuous or are above the jump, then I can also derive Steele's theorem globally, okay? Because the point is that if I know that on every degree in a cone, the function restricted to that degree is continuous, I have essentially a standard way to assign to that degree one real, that is one that codes the continuous function. And so this map, taking Turing degrees to single reals, has to stabilize on a cone. So we know that the continuous function has to be the same on a cone. And this only needs Turing determinacy, okay? But when alpha is greater than 1, and so when we have bare class beta functions, it's not clear if we can do it, because if we know that a function is bare class beta, let's say also just bare class 1, how can we canonically choose a parameter representing it? It would be like choosing a sequence, a canonical sequence of continuous function that converge to it. But it's not so clear how it can be done. So it's something we are working on.
Okay, thanks.
Okay,
Sure.
thank you. Are there any other questions? Any other questions from the audience? Okay, so then perhaps I'm asking a question. So a lot of your results strengthen some known results on uniformly degree invariant functions. Is there any hope that your techniques also do imply something about the case of degree invariant functions? I mean, not necessarily uniformly degree invariant functions.
This is it's a hard question because the most immediate reaction would be maybe no, because I mean, locally every approach for non-uniform functions would seem to be failing, because locally there is no, I mean, it might seem that locally there is no restrictions to functions. If Martin's conjecture is saying that on a cone functions have certain restrictions, it would seem that these restrictions are not coming from anything local, whereas locally I'm showing that some restriction there are for UDI functions, because these have to preserve a very I mean a very complicated structure that is the one of Turing equivalence via. Nevertheless, it happened to me to find some situation in which if some local property was true, then this would imply some fact about degree invariant function having to be necessarily uniformly degree invariant functions on a cone. So indirectly, maybe this technique would show that some functions actually have to be a uniformly degree invariant, even though maybe yeah, it's not so obvious. So okay. I hope this might sort of answer your question.
Okay, thank you.